Thank you. All right, so let's get going. So the session today is kind of the first of two sessions that I'm doing here that are very much tied together. They're all based around things happening with Windows and Windows performance. And so every year, when I start thinking about BriForum, I usually spend quite a bit of time preparing my sessions. And I actually started this last August with an idea of, yeah, I'll do something on performance next year, and why don't I just take a look at the different ways that Microsoft uses caching to improve the performance of the systems. And I'll do something like a top 10 list of those. And I started in on the work on it, and I realized, you know, I think it'd be nice to have like an ebook companion to go with it that talks about these topics and get some of it documented down, as well as all the great tools that you would use to look at the various ways of performance. And as I got about a month into the ebook, I realized that that didn't work. And it didn't work because all of the tools that we want to use are these GUI tools that need a tremendously huge monitor. You know, some of these you can't even think of looking at something that's less than a 1024 resolution. And your typical ebook is about 600 pixels. So there's really nothing you can do to get that down. I spent some time figuring, okay, I can just kind of crop stuff out and show this part of it, or I can show a big one and then blow up the stuff you actually want to try to read. And after a while, I decided that was crazy, and ended up just turning it into a book. Now, the book's not done yet. I've gotten very busy this year. And as I said, it started out to be the top 10 items that Microsoft does. The guide here lists it as the top 13. And I'm now up to the top 15, and the 15th is a list of about 7 more things I need to look into further. So we got more work to do. We got lots to talk about today, and I want to encourage you to stop me. I know this is Europe. You don't want to do that, but you know, it's okay. I'm American. You can interrupt me, ask questions, please. Okay? All right. I think I have to click once to wake it up. There we go. Oh, I didn't introduce myself. Yeah, okay, let me introduce. I'm this guy. Okay, so I'm Tim Mangan. My company's Team Immersion Technologies. My wife, Mary Jane, and I are 2/3 of the company. So we're a small place based out in Boston, in the US. We focus on the Microsoft AppV product. So if you are interested in AppV and need training, we're the people to come see. All right, so before I get into the top 15 list, I want to make one definition that I use, because what I'm trying to do is take a slice of everything that Microsoft does from a performance perspective, and I chose caching as a way to differentiate all of the millions of things that I could possibly talk about in Windows performance. But I want to define a cache specifically as a duplicate copy of something. Okay? And I want to contrast that with another term that I use. This is my term. No one else that I know uses it, called spoofing. And in spoofing, a lot of times we'll see things that vendors will call caching, but it's a very different operation. Specifically, we don't have a duplicate copy of something. Now, we'll see that come into play in a couple of the items that are on the list here. Okay? But primarily, the reason I bring this up is that when you hear something is caching, you're trying to figure out things in terms of performance and reliabilities of systems. We really want to understand, is it a cache or is it a spoof? Okay, so when it's a cache, you make a duplicate copy of something and put it somewhere where it's going to be faster to get access to it. Once we do that, we have to worry about cache coherency. How do you maintain and manage one of those two copies getting updated? And so that's your concern at that point. If something is truly a cache, do you, particularly if it's a new vendor producing something, you want to make sure you understand how do you manage when something gets updated. You think about your roaming profile scenario. That's an example of caching. And so you're going to have a copy on a server if you log out and that doesn't get removed. Now you go on to another machine, you know, your central profile gets the latest updates. You go to a new machine, you make changes, you log out, that goes up to the central machine. You go back to that first machine, you want to be sure that in most cases, and this will happen naturally with roaming profiles, that the new profile will get copied down to that machine. We actually take advantage of the fact that we have those old ones around sometimes, because if a user gets a corrupted profile, sometimes we can walk around the different terminal servers and find their old copy and copy it over rather than just blow away their profile. So that's nice. But in the case of spoofing, we really have to worry about what happens if the thing that was supposed to happen doesn't complete. And we'll talk about that and when we get into this. So this is the top 15 list now, 15th being an other category with a bunch of stuff in it. And we'll go through a number of these today. We'll bring up some tools and take a look at how we can view the performance aspects of that. But primarily, the main reason for talking about this now is that I think it's important to take a look at performance of your systems in well understood environments before you get the call that there's this huge problem going on at your company and they need you to go in and take a look at the problem. Because when you look at a normal running system, you're automatically going to see things that are going to look like problems if you're not used to seeing them. So you want to spend a little bit of time looking at the performance of normal systems in addition to when there's really problems out there. Okay, so we'll get to the first one here. And since it's an afternoon and everybody is very reserved here, I'm going to ask for a little bit of help here. I want to get you into the mood of raising your hand and saying things. So I'd like everyone to just think about being at a rugby match and or a football pitch and just start out with a big M. So everybody say M. M. Okay, good. All right. So everybody's awake. That's good. All right. So we're going to start talking about RAM. And RAM is kind of a weird one for me to talk about as being a caching, but in essence, it is a caching. When you run an application, it sits on the disk somewhere, it gets brought into memory, gets mapped in, and that is a copy. It's a cache. It's RAM. The reason that we do that is that the processor is able to access the bits so much faster than if it had to wait and get all of those instructions off of the hard disk. Kind of makes sense, right? But just as kind of an overview of the way virtual memory works, and this isn't specific to Microsoft, this is any operating system that's using virtual memory. We have a thing called a process space. So if we just leave ourselves in a 32-bit world here for a little bit, that's a 4 GB space that the process thinks it has and has ownership to, half of which will be that kernel space by default. Half will be the user space. And it allocates some memory for some of that stuff. We have another process that does the same thing. But the operating system, as part of allocating that memory, actually allocates virtual memory space. And so we can have as much virtual memory space as we possibly need. And these addresses just get mapped into a place, and then that'll get mapped down into some type of RAM location. Now, the amount of RAM we have versus the amount of virtual memory space can be completely different from each other, right? We can have a 4 GB process space and only have 2 GB of RAM installed. That's okay. If we start using up too much, instead of being in RAM, it'll get pushed out to a page file somewhere. But it'll still exist in virtual memory space. Okay? So that's our first entry. Whoop, wrong clicker on this mouse. Okay. There are some tools that we can use to look at things. This is a great, colorful tool that you can't possibly read from the back of it. This is the sysinternal's VM map tool. So this is one of those little tools that you can download. And basically, you start it up and you pick a process. In this case, I picked Dropbox.exe, right? I've got Dropbox on my PC, so that's the one I want to look at. And it provides a ton of detail about how that application is using memory. So at this top line here, this is called committed, and it's showing me that we have 91 megabytes of committed memory. Committed memory means the application has said, hey, this is memory I actually want to use, right? So it's going to try to use 91 megabytes. About half of that is marked as private bytes, which is that second line. Now, private bytes means that this is memory that wouldn't be shared by any other application. It's non-shareable. It's private to that process. That means I've got another 45 meg, roughly, that is shareable. Okay? Shareable is very important to us because this is how Microsoft saves a whole lot of memory. There are just tons of common DLLs that every application loads when it launches up. And what we want to have is just one copy of that DLL in RAM, and have the others share it. Because something is marked as shareable here, though, does not mean it's being shared. It just means that if someone else did happen to want those same things, it would be able to do so. Okay. We also have something called the working set. The working set is how much of that memory that's committed is in RAM and ready to be used immediately by the process without a page fault. So a lot of the RAM automatically gets paged out to the page file, and if it's not needed again, it'll stay there. That's one of the tools we can use. Okay, so number 2, can I get an I? Aye. Okay, not quite as exciting yet. Okay. All right, let's talk about the caches that we get inside our processors. So we have what are usually referred to as layer 1, layer 2, layer 3 caches. Now these have been being added to in the chips over time. Problem?
I'm just
okay.
see if the focus is good. Continue.
Okay. So these have been added over time. They have a tendency to get added first externally from the CPU, and then they get embedded into the CPU itself. So layer 1 cache is the fastest and typically the smallest of the caches. So if you think about the way the CPU works, it needs to run these operations, these machine operations. And it's going to do that on the basis of an instruction and some data associated with it. Now the data that the CPU needs to execute on will be based on the virtual memory address. The process code that we wrote and we loaded into memory is written against the process addresses. And part of the feature of the chips, of the CPUs, is to do the memory mapping, to bring in the appropriate pieces of the page tables, to change those out so that when the instructions go into the registers, that everything has the right address mapping and the instructions can happen right away. These caches here are how Intel and AMD do that. Okay, so the layer 1 cache is very fast. The CPU can retrieve or write to that memory location within 1 CPU clock cycle. Okay, so it's very efficient. DRAM, on the other hand, is extremely slow to go over the bus and get anything. And the way that the processors have gotten faster over the years has been by avoiding actually going to DRAM. So inside those CPUs is an awful lot of logic that takes care of prefetching all of the stuff that it needs into these caches. The layer 2 cache, it can vary, depend on the chip, but typically that runs at half of the speed of the CPU. So if the CPU needs to retrieve an instruction or data from that layer 2 cache, it actually has to pause for 1 instruction cycle and then get it. Okay? So it's a little less efficient. Layer 3 is typically somewhere slower than that. Okay? So it's going to be more than 1 cycle. But let me just get to the next example here. So we have some things we can do to look at this. So here, and the PowerPoint decks on this, by the way, will be available, I am told, a week from Friday up on the BriForum site. But this is a WMI query. So use the WebMTest tool, which is native to the operating system. Just go command prompt, WebMTest. It'll bring up a prompt. You have to connect into the machine. Usually the defaults there are fine if you're on the same machine. And then from there, you would find whatever table you're looking for. In this case, I asked for Win32 cache memory. So I called it a table. Technically, they call it a class. But if you think of it as being like a database table, where you have a table and you have rows in it, which here would be called instances. And then you have columns, which will be the detailed properties that we see here. So we can look at the values here. I did this on this particular laptop I have here. And I see that I have 3 entries here for caches. And when I look into the details, we can pull out the information that I'm showing down here in the bottom, showing what those different caches are. So in this case, I have a layer 1 cache, which is marked as a data cache. It's 32 kilobytes. I also have a second layer 1 cache. That's an instruction cache. And this is pretty typical with a laptop or desktop style processor. you're going to have both an instruction and data cache that are separated from each other at layer 1. A layer 2 cache I have here is called a unified cache, which means data and instructions can get intermixed as necessary. And that was a 3 megabyte cache. Okay, we can see there. Now I did this same test on a server I have. So this was a 2 processor, 6 core each with hyperthreading machine, right? So I see a whole bunch of entries in here, and basically I got 3 entries per physical processor that's on the box, so it was duplicated. And here I can see I got a level 1 cache, I got 192 kilobytes. Now there's only a data cache. I don't have a separate layer 1 instruction cache in this case. Now the main reason Intel decided to do that, my guess is the fact that I am using hyperthreading. Because I'm using hyperthreading, each of my logical cores is actually, or each pair of logical cores are sharing one physical CPU core that can actually run an instruction. So the problem of getting the stuff into a layer 1 isn't as much of an issue. It can go to layer 2 because you're always waiting one instruction cycle for the other guy to run anyway. So it's okay. That's kind of my idea on that logic. So then we had a 2 meg layer 2 cache, and then a really huge 122, that's an odd number. I'm sorry, 12. A 12 megabyte layer 3 cache on there, and that's shared across those. So that's something that really Intel is doing to help speed up the processing. Most of the advantages of what the processors have been able to do here in the last 5 years really revolve around these caches and all of the logic they put in to working with the operating system vendor to get the right pieces in place in those cache so that the actual CPU execution can be as efficient as possible and not be waiting for instructions. Okay, let's get on to number 3. Can I get a C?
C.
Hey, okay. All right, now, third one here is the hard disk controller. When we want to read something from the hard disk, and we're just going to assume spinning media here, right? You've got CPU, you've got your DRAM. Let's say we're going over a PCI bus to then to some disk controller and out to the disk itself. CPU is going to say, hey, I want to read something. It's going to go out through here, it's going to get to the disk controller. This controller is going to then have to position the heads, wait for the appropriate sector to get under it so that it can actually read it and send it back. That's what we refer to as latency, which is a variable number because it depends where the head happened to be. It depends on where it is in the rotation process and all of that. But we do put RAM on these disk controllers to help speed up, and this is a case of caching. So when I make this request out and I do that read, well, you know, that head is positioned over data an awful lot of time, and as it's waiting for the right sector to come up, and then shortly afterwards, if it doesn't get another instruction, it's going to read additional sectors, and it's going to put them into its RAM cache, hoping that you're going to come back and ask for it soon. And if you do, when you make that read, the disk controller is smart to say, oop, I already have that one here, there you go. And your latency is very, very small for that particular transaction. So that's a case of caching. The disk controller is properly constructed to take care of the cache coherency problem, that if I went and wrote that information, it would notice that and it would invalidate its cache copy in RAM. So we'd be okay. Now when we go to do writes, that's where it gets a little funky. Okay, so we got 2 types of writes that can happen, generally called write through or write back. Write through is a case of proper caching. CPU says, hey, I got this data to write. It'll get DMA'd over, get to the disk controller. Disk controller, in the case of write through, will put it into RAM. It will then commit it to the disk and actually getting it out on the platter. And when it's done getting it out to the platter, then it will respond back and say, hey, I'm done. It'll retain that copy in RAM in case you then ask to read. Why not? It had to put it there to begin with. And that's great. That's a case of caching. Again, the disk controller takes care of the coherency issue, not a problem. Write back is another story. This is the example of what I call spoofing. We set up, we say we want to write it, the disk controller gets it, puts it in the RAM, and immediately says, hey, I'm done. and then it writes it out to the disk. Okay? So what happens if, now again, until it writes it out to the disk, there is no copy. There's only one copy of it existing. So what happens if we lose power on this machine at that point? If that's just traditional RAM on a disk controller, we've lost that data. It never got committed to the disk, and you may have a corrupted file system now. So this is one of the reasons why we generally recommend you don't use write back unless you have a battery backed RAM on that, or if it's like I have on the laptop here, it's a flash-based, so that I do recover from the loss of power in the middle of the transaction. Okay. So some tools that we can use looking at this stuff. I mean, iometer is a tool if you're really looking at just plain raw performance in general of the disk I/O system. This is another tool that I like called Performance Test. It's from Passmark, which is an independent organization, passmark.org, and they produce this. And the reason I like it is that it does some benchmarking using different style of patterns of reading and writing that we can look at. So this particular test I ran on this laptop. So I bought 2 disks for this laptop that are identical in every way that I could possibly make them, except one had a RAM cache and one had a flash cache, because I wanted to take a look at that. It was a hybrid drive is how they market that. I want to look at the performance, and the flash drive, generally speaking, turns out to be much better, right? Same specs for everything other than the fact that that had flash on it. I'm getting about 50% more performance here. So in the overall disk mark, this was at 572 whatever per second, and this was at a little over 400. So it's almost 50%, I'm sorry, 40% improvement in overall performance. We look at things like sequential reads, definitely hits that mark. The one area that was kind of weird when I ran this test is when I looked at random seeks and then a read-write operation. And it actually turned out that the non-flash drive was a lot faster, which really surprised me. But you know, how much of that do I really do? I don't really think I do that much of just random read-write seeks. It tends to be fairly sequential reads and writes, particularly on a laptop device. So I'm not too concerned about that. One thing I do like to point out, which is another piece of the I/O caching involved with Windows machines, is what the operating system is doing. So this is an example of a test. So this is the PerfMon, you know, the performance monitor thing you can get now, actually right out of the task manager, right? You can get the advanced stuff. And I added in, I brought in 2 counters here. One is called dirty pages, and the other is called lazy write pages. So dirty pages is basically the cache inside the kernel as you go to do file writes. So if you change something and you want that committed out the disk, it first goes into the dirty page pool within the kernel, and from there it then gets written out to disk. And Microsoft kind of buffers that stuff up a little bit. So in this particular case, I took a very large file and I copied it from one partition to the other, and we watched these counters. And so it read in the file very quickly and put everything into the dirty page pool, and it actually goes off the screen here even higher. And then slowly we see that come down. But if you look at the actual writes that are happening out to the disk, you see that's a very spiked transaction. The kernel has a thread that wakes up once a second and looks at the dirty page list and decides how much it's going to write out. And so even though I do the copy operation, I get the little graphic wizard saying copying, copying, copying. Okay, that copying ended about here from what I could see in the user interface. Okay, everything was into the dirty page is what that meant, and the operating system was still committing that out for another 10 seconds after that, I think, until it was done. Okay, so that's another example of what Windows is doing in caching. That clock was not moving. Oh, okay. Okay, MIC. Can I get an R? R. R, okay. Ready boot. I'm not actually going to talk a lot about Ready Boot in this presentation. My presentation tomorrow, we actually walk through in great detail the Windows 7 and Windows 8 boot, and Ready Boot is part of that. So I'm going to leave that one for tomorrow, but I'll give you a quick teaser here Microsoft uses ReadyBoot as a way to speed up the booting process. And this is particularly important in the case of VDI, where we want things to spin up using as little resources as possible and as quickly as possible so that they're ready for the user as quick as we can get them. Part of what you'll see in the presentation tomorrow is this chart and the Windows 8 version of it that walks through the boot and sleep and hibernate process. Oh, wow. I didn't know I had that animation in there. And then there are some tools that we can use. So Microsoft records a lot of information about the boot process directly in the event log. And there are things that we can do to find those things. But I have a new tool. No, I forgot to bring that up. I have a whole bunch of new tools and updated tools that I'm releasing in conjunction with the session here today. I want that window. There we go. To get at those, I'll try to remember to mention which ones they are. Just go to www.tmerchant.com. You click on the tools link right there. I got to get my mouse over. And then I've got a whole bunch of tools, not just these. So you kind of have to scroll down until you get to the thing right there that says the performance tools. Okay, so I've tried to put them all in one place here. And this is a list of all of the tools that I'll be covering today. Okay, so if you want the actual URL, it would be tmerchant.com/tools/perfTools, P-E-R-F tools.aspx. Oh, yeah, and they're free. Yeah. Okay, so this is a new tool that's called What's My Boot? And it takes a look at all of the information that we can get from the registry and analyzes the performance of your boot. So you can see how long the boots take, which is sort of this chart right here, broken down as to how much is the main part of the boot and how much is the what they call the post-boot mode, when the operating system continues to do a lot of work because you booted, but it held off the processing. And then the performance of the actual caching. And what you'll find, and this is where it becomes important for VDI, your initial boots are quite lengthy in time. But the operating system learns through ReadyBoot how to improve the performance by using this caching. As you can see, we can, just by booting our machine, typically about 5 or 6 times after you've gotten your golden image ready, you can dramatically improve the boot time. So. Yeah.
When is the boot process considered complete?
Okay, Microsoft considers the boot process complete starting from a time after the user has completed the login, the first user login, and the desktop appears. They then wait until there is, I can't remember the number, I think it's like 5 seconds of CPU activity of no more than 20% of the CPU. So basically waiting for the whole everything to kind of calm down a little bit. So when measuring boot time, if we're trying to do measurements like this, we don't want to use it with a real user, right? Because they will start Outlook up and use up a lot of CPU and really skew the results. So looking at real user times on this, you have to kind of discount that depending on what they do. But if you're looking at just trying to compare 2 different implementations about which one's working better, then you can have an automated login type of scenario and get really good numbers out of these.
Would it be applicable for a server operating system as well, such as Windows Server? You would have a SQL server or something, you want to measure the boot time?
I suppose, but how often do you really boot that machine? And are you that concerned, right?
Right, okay, yeah.
Yeah. Okay. Some other tools to talk about on this. So when the operating system creates the boot plan, it gets put into the registry. We haven't actually figured out how to decode that properly yet. That's something I'm still working on to figure out what they're putting in there. But we can see some of the effects. One of the great ways to do this is to use the process monitor from sysinternals. So this was a new thing to me that I'd never noticed until I read about it. You start up the process monitor, you go in the options menu, there's this thing called Enable Boot Logging. You click that checkbox, you'll get a little thing that says, you got about 10 seconds and I'm going to reboot you. It reboots and then it records all of the monitoring information. So it basically, before the boot, tells the operating system, hey, I want all this stuff recorded. And then after the, I believe it's 90 seconds after the system declares the boot is complete, right? So about 180 seconds after the user logged in typically, then that finishes up, and then we can use another tool called XPerf, which comes from the Windows SDK. So the Windows SDK is something you can download from free from Microsoft. You don't need to install the whole SDK. All you need is the performance tools a part of that, and you get XPerf. XPerf produces a ton of graphs that are kind of like this, looking at various aspects of the booting performance. Now, this particular graph right here is showing the caching that it did in pre-caching for Ready Boot. But if I saw a particular problem in an area, you can go in and you can drill down into these and get great detail. So it's great for finding things like you've got a bad driver that's slowing down your boot. This is the easiest way to find out what driver is it, and then get that one replaced. Okay. MICR. Can I get an O? Oh, okay. Cache Manager DLL sharing. Oh. This was one of the, it should have been the easiest chapter for me to write in the book. Okay? I have done sessions at BriForum in years past on this thing. I sat down, I wrote it out. It was about 5 pages in the book. I put little placeholders where, okay, we'll run this test, we'll run this test. And I came back about a week later and I ran the test to get the screen captures to go in there. It didn't work. Something was wrong. So I spent about a month trying to figure out what was wrong, because I know this test works. I've done it on stage. It just didn't work. It turned out that Microsoft made a change, had absolutely nothing to do with this topic, and had tremendous impact on it. So what was the test I was doing? Okay. I talked at the very first section about the virtual memory and how we do sharing of DLLs so that only one copy exists in RAM. Well, that works great when it works. But when the developer creates the DLL, they have to give a base location for that DLL to load into. So that's the address within the process memory space that it wants to get loaded to. And as long as that address space is free, it just gets loaded right into there. We get DLL sharing. Everything is wonderful. But sometimes, you know, these DLLs are shared, and a program loads it up, and something else is already in that location, because there's only a limited number of locations that developers typically try to put these things at. So when that happens, the operating system covers us by doing what I'll refer to as rebasing on the fly. So basically, it loads the DLL up, but then it has to walk through a pointer table of changing all of the addresses based on the fact that it's not based where it was. And the PE format of the executables provide the instructions on how to do that. It's a fairly efficient operation, except that it causes a duplication of the DLL in RAM for every use. This happens due to what Intel calls copy on write memory. So when the DLL gets mapped into memory, it gets put into what's called copy on write memory. And then when the rebasing happens, it notices that the fact that, oh, you're trying to write to a page that's marked as copy on write. Well, I'm going to make a duplicate copy of that memory page, give it a new virtual memory pointer, and then allow the write to continue in there. So this is a kernel interrupt that happens to cause this to take effect. The effect of this is that every single one that gets loaded in gets its own copy of the DLL, in essence. Not the entire DLL, but most of it. So I developed a tool a number of years ago that was basically a DLL launcher that you would pick 2 DLLs and then hit a button to have that loaded into memory. And then we'd take a tool that would take a look at the amount of RAM you're using and the memory usage, and we would watch this guy spike up. And typically, what I expected to see, what I've always seen in the past, is I created a DLL that was 100 megabytes in size, called massive DLL, and then another DLL with the same address. And so if I loaded the large DLL first and then the small DLL, ran that, and then I did it again in a second process, I would see a chart that would look very much like this. On the first load, I'd see 100 megabytes come in. The second load, I wouldn't see anything. If I did them in the other order, because it was the second DLL that was being rebased and it was very small, to explain that. If I did them in the other order, and I loaded the small DLL first, and then the big one had to be rebased. And what I used to see and expected to see is I would see this first spike up, and then I'd see a second spike. But when I ran these tests, it didn't happen. It took me about a month to figure out why. The reason why is Microsoft, a number of years back, implemented something called Address Space Layout Resolution, ASLR. This is a feature they put in for security purposes to get DLLs to load into quote-unquote random locations. Random doesn't really mean random. It means a small list that it decides where to put it to. When they did that, they actually fixed this problem that I was trying to show here. And it was a big surprise. Now, Citrix, how many people here use ZNet? Right? A lot of you? Okay. You remember a number of years back, there was a company called RTO Software, and Citrix licensed some technology to them from them. And it's a checkbox called the memory management thing. Okay? That was all about this topic right here, solving this problem. They would solve it by watching which DLLs have the problem and then rewrite the DLLs so they wouldn't have the problem.
Isn't that in the FB as well, rebased DLLs?
Yes, but nobody uses it.
No, I don't play
And you shouldn't.
But it's there.
But it's there. But this doesn't work. So what happened is when ALSR is in use for a DLL, it gets loaded into a random location, which means all the rebasing happens. It's not copy on write memory. It does all the fix-ups once. So now, whenever anyone else wants that DLL, the fix-up has already happened. And presumably, it would be a location that wouldn't be in use by something else because every DLL that gets loaded, the operating system is picking a place that knows would be a different place. So that works out pretty well. What happened in addition is that in Visual Studio 2003, they added a feature to allow developers to opt out of ALSR. But that feature is off by default. So basically, if someone had some code that really was location dependent and it would break, then they could opt out. But by default, anything that's been compiled in the last 5 years has ALSR enabled unless the developer did something special. So basically, this problem has pretty much gone away except for some very old legacy applications. The memory sharing that's going on in RAM now is much more effective. And in fact, Citrix has told me that they're taking that feature out. I don't know when, but they're doing it. Okay. Another tool I haven't mentioned yet is VMMap. So earlier we looked at RAM map, which looked at a particular process and allowed us to see what was going on. A VMMap, which is also this funky color thing here, allows us to look also at a process. But we can get into more of the details. In particular here, we can see whether or not that DLL is using ALSR. So if you are having a rebasing issue still, you would be able to use this tool to find out which DLLs at least might have that problem. Right? Every time you, if you try to look at the rebase counter out of the operating system, the first load of the DLLs will always cause those write-on-copy events, but it's just happening the once, and it isn't really using more RAM.
I think Citrix said 25% or something as a sort of an average for memory saving.
For savings?
Yeah.
Okay. It might even be more than that. Yeah. Particularly on a terminal server, it should be much more. Right. Okay. MICROF. Okay. F. Okay. All right. Pre-read sequential I/O. The Windows Cache Manager is responsible for dealing with all of the files of the operating system as you try to read them in. It has a particular feature to try to speed up reads. And you need to be aware of this if you're trying to do some performance testing. Basically, it looks for examples of sequential I/O. So you're reading a file from the beginning to the end, or maybe even from the end to the beginning. Makes the first request, makes the second request. Upon the third request, in the case of Windows Vista, second request in the case of Windows 7, it then immediately requests the next block. Okay, so when it detects this pattern, it says, oh, you're asking for this one. Well, I'm going to get this from the disk, but I'm immediately going to queue the next one. So it's in process already, and I'm bringing it in before I get the request. And this does have a significant impact on the performance. It not only does this in the forward direction, it also does it in the backward direction, and it also doesn't need to be exactly sequential. If for some reason someone had an application that read every other sector, it would also detect that pattern. I don't know how common that one is. All right. I developed another free tool. This one's called Sequential Read, which gives you the opportunity. I like to develop bad tools that work in a particular way, right? And this is an example of that. So here we can pick a forward, backward direction, or a random direction, and just ask it to read in the file, and it'll tell us how long it's taking. So in this case, I'm also reading a counter that tells me how many read-ahead IOs, which means how many times did the cache manager actually do that read-ahead to improve the performance. So in this case, I read in the exact same file 3 times, after, of course, making sure I got it completely cleared out of the cache. I had to have PREFETCH off, and I actually rebooted in between these as well, just to be sure. So in this case, I read in a random direction. It took me 172 milliseconds. I read in the forward direction. It took only 47 milliseconds. So about a quarter of the time to read in that file. And we can see here, I actually, in the random, I got 178 read-ahead attempts. So it actually detected enough to do some pre-reads for me. Whereas here I had 629, and there were only 630 buffers. So I can see that it was actually doing it immediately as soon as I got that second packet in. Here I did the reverse direction. It took 484 milliseconds. Actually more time than the random time, right? This was 172. This is 484 milliseconds. I had 627 read-aheads, which means after the third one, it figured out that there was a pattern here and went to it. But it still took a lot longer, and that's because of the rotation of the disk. I'm reading a sector, and what I want next is the sector that was just before that. And so typically the head's moving in, I get the sector I want, it can cache the next sector into the RAM of the controller, but I can't get that effect when I'm doing this backward reading. So it is much slower to be doing that backward reading. About the only use of this is like if you're reading log files, a lot of times the software, if it's a log file reader, will read the end of the file first to present that to you quickly, because that's the most recent information. But most apps don't do that. Okay, 7. Where are we? M-I-C-R-O-F-T. Right. Oh.
S-O-F.
What letter am I on?
You're now on the second
Oh, okay, give me an O. Okay. Let's talk about standby lists. This is an area that gets into performance quite a bit. So as the operating system is running, it wants to free up memory for potential use in the future. And so it will look at memory, and it will randomly pull things out of the working set lists of processes and say, I want to write this out to the page file. It does not care whether or not you've been using that particular page of memory. Once upon a time, it did care. It had the ability to take a look at whether or not that memory had been accessed before it put it out. But that's when we had single processors and a much simpler version of the operating system. So today, it just randomly takes pieces of memory, whether or not you're using it, writes it out to the page file. When it does that, it doesn't get rid of the memory. Okay? It simply removes it from the page file and adds it into the available memory pool in one of the standby lists that it has. So as of Windows Vista, we have 7 different standby lists that it can go to based on priorities. And as memory is needed, things will get pulled out of the standby list. But if they're needed again, they're able to come back very quickly because there's no disk I/O involved with the process. So I think my next slide is a visual of that. Yes. So here we have a process. We have its working set list. So all those orange boxes are the pages of memory that it's currently in its list that it's using. We've got a page file down here. And once a second, something called the balance set manager, it's a thread within the kernel, wakes up and looks for some memory to take. And so it puts that into the modified page list queue, and then that will get paged out to disk. And as it does that, it will then put a copy, there we go, into a standby queue. Now, as I said, there's 7 of them, and normally it's going to go into standby queue 5 when this operation happens. if the process suddenly needs that page of memory again, a kernel interrupt happens that we refer to as a page fault. Okay? If the operating system finds that the page it needs is currently in the standby list, all it has to do is change a couple of bits to put it back into the working set list of the process and remove it from the standby list. So there's no I/O. It's a very fast operation. We refer to that as a soft page fault. Okay? Soft page faults means that your operating system is operating very effectively. It's doing its best to conserve memory for you, but it's not really impacting performance very much. What we're concerned about today are hard page faults, which unfortunately there isn't a counter for. There's a counter for page faults, and there's a counter for soft page faults. Hard page faults could be the ones in between, but typically, rather than do arithmetic, we just look at pages in from the page file. So we just look at that counter, then we can see what our hard page faults are. And that's the counter you should really be concerned with if you're thinking you're having a paging problem.
Sorry, why are there 7 lists and not 1 or 5 or? Because Windows adds version 7?
No. So part of it has to do with another chapter here about PREFETCH. Okay, but Microsoft in Windows Vista implemented memory priority, and it's a feature that is very much not used. Okay, but the idea is that when so we have these 8 standby lists. Yes, it's 0 through 7. There's 8 of them. We've got something called the free page list and the 0 page list. So the 0 page list is memory that's immediately available for a process. If a process says, hey, I want memory, it's going to grab it from that pool. That is memory which has been cleared out. So we know it has no contents from its previous use. You know, if I had an application, I wrote my password in it, it freed that memory up. I need to be sure that that memory gets cleaned out before it gets handed to another application, which could then try to snoop and get that password. So memory is always allocated to applications out of the 0 page list, except for a special case it can come out of free page, but that's only because it's a driver and it knows it's actually going to overwrite the whole memory anyway. Free page list is what's ready to be zeroed out, basically. Okay? And basically, as you start needing memory, it will grab things starting with standby list 0, move it into the free page list, and as it gets a chance, it'll zero it out. The thing that actually does that zeroing, by the way, you know that system idle task? Task ID 0. If you ever look at it, you'll see you get 1 thread per physical processor. And basically, that's your free run when the processor has nothing to do task. Okay? It runs. Its primary job is to zero out memory into the 0 memory pool. Okay? So we sometimes refer to that as a 0 page task. The 0 page thread. Refer to it. Okay, so the purpose of the different lists here is so that things that are less important can get cleared out first, as opposed to older, right? So most of the stuff goes in standby list 5, which is referred to as the normal priority. PREFETCH will do some things to put things in either lower priority, or there are some things the operating system will actually put into the standby list automatically in a very high priority to try to keep it from being flushed out unless you got into a really severe memory crunch. All right. Other tools that we can look at is I've got a free tool. It's been out for a number of years here called ATM. I developed this specifically to look at the Windows Cache Manager. That was a BriForum session a number of years back. But it gives you a nice look at these different memory pools that are in there and how the cache manager is operating from a graphics standpoint. If you want to do some of the testing that I do to clean things out, right? So if I'm trying to test one particular style of caching, like when I was doing this sequential read, I said I would disable PREFETCH to keep it from prefetching stuff in. But I'd also come in and clean out the cache manager down here with one of these buttons. And I can say, just clear out everything out of the standby caches, clear out everything out of the system cache, and now I can run that test and ensure that it's actually not in memory behind my back, and I'm getting the effect that I want. This is the tool RAMMap, okay, which is that other of the sysinternal tools. This provides us real detail where we can actually see what files are in memory, including in those standby lists, And if we drill down into a particular file, we can see which of the standby lists it's actually in. So this is how I figured out that most of the stuff is going into priority 5. An entire file doesn't need to be in the same standby list, by the way. They can be different priorities based on how those particular pages got mapped in. And I'll see that happen sometimes. SuperFetch will first start bringing in stuff, and then as I actually start running that application, we'll get some other demand pages that come in, and they will be at a higher priority because SuperFetch didn't bring them in. It was actually the process. Okay. So some other tools that I have involved in this area, these two are older tools. These are tools to produce specific problems. This one's called leak memory. So if any of you are using EdgeSight to monitor your systems, you're looking for processes that leak memory, this is a tool that you could use to make sure that you're actually catching them, right? Run it as a test, make sure that you actually do catch this process, then you'll know your system is set up and will do what you want here. This one's called Page Mania, which basically causes a ton of paging activity. So if you want to, again, have a tool to make sure that it's monitoring properly on your system for heavy paging activity, you could use this tool to cause that. You could also use it as a way to simulate, okay, I think I'm having a problem like this, but it happens once every 3 days on a particular system. Let me run this tool and see if the symptoms look the same, right? That's another use. And then this tool down here is a new one. It's called dprio, and this provides you the ability to read a file into memory at a different memory priority. So you can set the memory priority in here, load the file in, and see how that works. Okay. Oh, I must be on F now? Can I get an F? F. All right. Okay, SuperFetch, my favorite feature of the operating system that everybody hates. Okay, SuperFetch is about watching long-term patterns that a user access different files and anticipating that they're going to want them again. So what the operating system is doing is it's watching particular kinds of events and what happens immediately after. User login is the primary event we see this on. But also for reboots, coming out of hibernation on a laptop is another SuperFetch event that's very important. And it'll look at those things, and then when the event happens again, it will immediately start reading those files in off of disk into memory in anticipation that the user is going to do the same thing again. So on my laptop, I open it up, I log in almost every time I launch Outlook as the first step. Okay? SuperFetch knows this. I can boot up my operating system and log in, and there will be a lot of disk activity, and if I pull out tools like RAM map we saw earlier, I will see my Outlook PST file loaded up into RAM, ready for me, so that when I do launch Outlook, it'll start up a little faster. Okay? Now, Microsoft is a little over aggressive in the way that it pages this stuff in off a disk. And that's the main reason that people hate this feature, is that they do start up and they just log in, they see all of this disk activity, and they think, oh my God, I just don't like this, and so they disable the feature. Now, some of the features that we've been talking about are intertwined. The Microsoft implementation, specifically for SuperFetch, Ready Boot, and Ready Boost, are all intertwined with a lot of the same drivers and code and services. If you turn off the SuperFetch service as a way of getting rid of SuperFetch, you also affect those other types of caching that they're doing. Okay, so you just need to be aware of that. Okay, so what does it do? Well, it reads those files in off of the scenario, and it's going to read them into those standby lists, typically at a little lower priority. So this is an example of the ATM tool shortly after my login. I just logged in, didn't do anything, and just let it sit there for a little bit. And I certainly saw that after, so this is about 60 seconds, so I'd say about 20 seconds after login, I start seeing these standby lists start to increase in size. And that's SuperFetch bringing those extra pieces in. In here in the orange, this is the higher priority memory. So these are things that are kind of common across the system that it expects me to use constantly, and it wants to try to just bring them into memory and leave them there so they're ready to go. And then this is, probably my PST file is primarily this white area here, right? So there we can use a tool like that to see the effect. Again, we can go into RAM map, and we can pick in, and we can actually see, in this case, I'm looking at I can't even read what that is with that focus. But some file here that's been read in, and it's coming in at priority 4, which is a step below that normal priority that most of the running applications would go into the standby list. I also have a new tool down here, whose name I have to remember because I hit it. Oh, SuperFetch list. I got it on the screen here. Good. I tried to make it a little bit bigger, and I actually accidentally got the label underneath there. So SuperFetch list, I'm in the process here of decoding what files SuperFetch is going to cache in. So I've got a tool that'll do that now. As I said, there are multiple scenarios that they use, and I actually haven't figured out entirely which file is which scenario. But I have a tool that will display all of the files that will read in some scenario and in which of the scenarios it is. So it's still a little bit of a work in process, but at least for the first time now, we can see what's going to be read in, and we can start to get a clue as to what those things are. So it's kind of a, stay tuned, this will get a little better, but.
How much impact does SuperFetch have on machines running from SSD rather than operating system? The big problem with standard hard disks is latency to get to the data, to move
right.
ahead and everything.
The general advice is with SSDs, you want to turn SuperFetch off. And that's really more of a, we're still not 100% sure about the wear patterns and all that, so why read it in if you don't need to kind of scenario. I mean, for performance, it's always going to be better to have it in memory, particularly with how much memory we jam in our machines today, right? Your typical user machine, you're going to have a lot of memory, and you're really only using this much, right? Typically, half of that memory, it may be stuff that's sitting there in the standby list because of SuperFetch. And if you don't use it, it's free memory. It looks nice to see, ooh, I've got all this free memory, but your performance is actually worse than if you had read that stuff in. Right?
Could you disable things in there if you want to?
Oh God, I wish I could. That's one of the reasons that I've been working to figure out how to decode the format of whether these DB files, which is where SuperFetch stores this information. And it's been a lot of work to be able to code it. So I've gotten to the point now where I understand the format of the file and I can list this stuff out. I probably could even create a new file if I wanted to build an editor, allow to select and do that. Not quite at that point yet, but I'm thinking longer term in the future. Like right now, particularly in VDI, we also recommend you turn off SuperFetch. I'm thinking that SuperFetch is probably a really good technology for VDI if we could control what it's going to read in. Right? So I'd like to get there. But maybe someone else can pick up the torch and do that. We have a lot of vendors here, They make money at this stuff. Me, it's just my free time. All right. 9, can I get a T? T. Okay, good. All right, application prefetch. So SuperFetch is about bringing stuff in anticipation on long-term patterns of use global across the operating system. Application prefetch is the same thing on the level of the application itself. Every time you run an application, the operating system takes a look at the I/O patterns that happen from the process that's loading the application, records that into a file, it's a .pf file in the Windows prefetch folder, and saves that off. And the next time you launch that application, the OS will automatically read the PF file and start pre-caching all of those DLLs that got loaded in there. DLLs and any other file that the application reads, right? So it'll read that back in. You'll find it saves, it's a limited number. I can't remember, is it 20 or 50? But there's a limited number of applications that it'll save in there. It's smart enough to detect differences in some particular applications like mmc.exe. You may launch one way in one particular use because you're bringing in certain of the panels, and you may run it a different way from another location. It's actually smart enough to catch that and will record both of those MMCs as separate entries in here. The entries always have a name and then a hash code about the path of the thing that actually launched it, so it does that detection. But it does improve the performance of the application launches. So I have another new tool called Load DLLs, which is actually being shown, a portion of it down here at the bottom, that will load in a folder of DLLs. You just give it a folder, it'll load them all in, and it'll give you a timing on that. And so one of the tests I did here is I ran it for the first time, making sure there was no, I'm sorry, this was the case where I loaded it multiple times, and this was one of the last runs that I did, and it took 172 milliseconds in this case to read in 102 DLLs, right? I then went into the PREFETCH folder, deleted the PF file just to see what the difference is and how effective this is, and it took 407 milliseconds to do that same operation. So this does significantly impact the app launch performance, and it's a good thing to have in there. Along that line, this is a tool called the Windows File Analyzer. So I actually found this from some folks that are more into the computer forensics world. They're real busy trying to figure out what people are doing, and they found the application PREFETCH as an important thing for them to go look at. It does have information in the PREFETCH files about how many times you've run this application, when the last time you ran it was, and things like that. And so you can actually run their tool, ask for the PREFETCH files, and it'll actually show you. So I can see that I've run this 10,000 times. What's that? Oh, that's the search filter, right? Part of the operating system. Okay. But you know, here we can see DLL host. Actually, right. This is sorted by use, so the top ones are all just standard operating system things. But if you went further down the list, you'd be able to see particular ones, and that seems to be of interest to those people. Okay. Can I get an S? Yes. Okay, good. All right, number 10. How am I doing on time, by the way? Oh, when am I supposed to end? 20 past. Okay. Well, we're on 10 out of 15. I'm not sure I'm doing so okay. All right, ReadyBoost. ReadyBoost is another useless Microsoft caching technology that nobody is in their right mind is going to use. So ReadyBoost is about having a USB drive, right, taking a flash drive, and using it as a way to help solve the rotational disk latency issue. So basically, you plug it in, you train it and say, hey, I want to use ReadyBoost with it. And what it'll do is the operating system will watch your I/O patterns, and it'll look for very small files that you frequently access, and it will make a cached copy of them on the USB drive. And now the next time you go to ask for it, it can pull it out of the USB. Theory being, rotational drive, large transfers, that latency issue isn't as big due to the pre-caching, the controller, the read ahead on the cache, all of that summary of stuff. It's not that bad, but a small file you ask for is like one sector of disk. You're hitting that entire latency hit to do that. So those are the ones they want to put on the RAM drive, the flash drive, where the time it takes, there's no latency associated with reading off the flash. The whole time is really associated with getting across the USB bus. And that's much smaller compared to anything on a rotational disk. So those operations happen very fast now. You wouldn't want to do a large file there because the USB bus becomes a bottleneck as you try to do lots and lots of transfers over it. So they decided it was more effective for these small files. So it'll automatically cache those things onto there. It does a great job of taking care of the cache coherency problem and managing that. And the data that goes on there is fully encrypted. Now it's fully encrypted on a runtime key generated when you booted, which means that if you pull that thing out, it is now completely useless. The only one with the key will be the machine you're on. So as long as you don't reboot, you can put it back into that drive and it can reuse it. But if you reboot while it's out and put it back on, it basically, first thing it does is delete the file and start over. If you pull it in another machine, it will delete the file and start over. So they feel that this is very secure. And in fact, those forensics guys are looked at it and just said, well, we can't use that one. So they're not looking at it. So if you had a really underpowered laptop, it could help a little bit. But the performance boost is very, very small. It's not really worth the effort as far as I can tell. Okay. But in case you do care, I have a new tool. This is called Ready Viewer. It will analyze the information about the flash drive if it's currently workable. Okay, so we can see how much of the space is being used, the compression effectiveness. So in addition to it being encrypted, that data is also compressed on the flash as well, since our CPUs are fast enough that that makes it worthwhile. And we can dump some information out from there. Can't see what files are in there, right? Because I don't have the encryption key, but that we can do. Okay, so 11 must be, give me a U. U. Okay. All right, file directory cache. I'm not going to talk a whole lot about this one, but basically the file directory within your partition, the operating system, there's a file called the MFT that will get read in. And the operating system pretty much will cache that in RAM inside the kernel. In fact, we can see this happen most often if we go to an idle system, go to the Windows Explorer, and rename a file. That rename operation will happen immediately, typically without any disk I/O happening. Okay? It will make the change to the MFT in RAM, and eventually it'll flush that out to the disk, but it doesn't feel that it's all that important to do it right away. Okay? If I open up a Windows Explorer, if I had it open and I do a dir command, without it writing to the disk, I will see the new name of that file show up in a separate process as well. So it's all handled very well in that fashion. But part of the boot down process is actually flushing out all the dirty pages, and it will make sure that it commits that to disk before it finishes the shutdown. Okay. Can I get a C? C. Okay. The internet cache. Also not going to spend a lot of time talking about this one, because everyone knows the internet cache, right? You go to the internet, 5 minutes, 10 minutes, 10 minutes, 2 hands, okay. You go to the internet. When you make a request to go see a page on the internet, there are a lot of transactions involved with that. So let's say I go to, what was this page? Probably not that one. Let's go to the previous page. Where's the mouse? Okay. So when I ask for this page, right, first thing is just ask for the page itself. And so a whole bunch of HTML comes down, but that HTML includes references to images like this, and this, that then the browser goes back and gets from wherever those sources is. And they can be from the same server, could be from another website, right? I can have my own page here, but I can have an image that comes off of BriForum.com if I wanted to, right? And I could have that as kind of a mashup that happens here. All of those things are separate files that then get cached into your internet cache on the hard disk. The next time I come to this page and I ask for this page, I'll get the page, and then I'm going to go and I'm going to ask for, oh, I want this image. Now, on any of those requests, as part of the request to the server, if that particular file or page is already cached in my internet cache, part of that request says, I want to get this page, and oh, by the way, I have a copy, and here's the date stamp. The server will then either return the page to me or an indication that says, oh, you've already got the latest, right? Which is shouldn't say error code, but code 300. So then it'll just take the copy off of the disk and bring it up. So that's a form of caching that dramatically improves our browsing experience. If you go and clean out your browsing cache, you will definitely see a much slower page loading the next time you bring up any particular page that you're used to going to all the time. Okay. Of course, you also lose your cookies. You have to log in again. Oops, right. Okay, there's that one. 13. Can I get a K? K. Okay. All right. User profile caching. Right. Roaming profiles. This is another particular area that Microsoft uses caching to improve performance. If you're using roaming profiles, so when you log in, if you're in a roaming profile environment, that means your profile is stored up on a profile server somewhere, and as you log into the machine, it's got to copy that entire profile down to the local system before your login gets to complete and you get your full desktop experience. That can be a very painful process. That's why if you're using roaming profiles, you want to get as much of the stuff as you can out of that profile, get that stuff redirected into the user's home drive so that it doesn't come down upon login, but is actually accessed on demand, right? So we want to do those things. Yeah, that's all I want to talk about that. We'll see if we can leave time for questions. GPU, where am I? Can I get an S? Yes. And what does that spell? Somebody was paying attention, good. Sorry, I just threw that in there. All right, GPU caching. This is a new kind of cool area that I'm really interested in. So the GPUs are extremely powerful processors in a different kind of a way from a CPU. A CPU is designed to be able to run a set of instructions from a wide set of instructions and do it very fast and efficiently. But the GPU is designed to run an instruction multiple times in parallel over a large data set. The kicker is that you want to have enough of a data set inside the GPU in its memory, because it has RAM as well, right? That acts kind of like a one of those layer caches that we had earlier on the CPU. And there are some people who are starting to develop applications that take advantage of this. And so if you have the right kind of applications, and the right kind of applications are things like weather applications, things with large data sets that they can control, where they want to run a whole set of things over this large data set and in an iterative kind of a process. That's the perfect kind of application to be running inside of a GPU. And so they're making use of the APIs that the GPU vendors provide to be able to load these things in and run, and they're able to run stuff that is like, 100 times faster than what you could possibly do in a CPU. And that's kind of cool. I kind of like that. Now, sysinternals came out with a new version of the process monitor this year that allows you to take a look at the GPU performance. So we can go in, particularly with, this is a kind of a boring GPU here, but particularly some of the newer GPUs, if you look at the stuff that the vendors are doing to do GPU sharing in the server, so you can get a GPU that has multiple cores within it, and you can basically get a virtual GPU for multiple either VDI or eventually probably terminal server type of loads in there, where you can assign the individual users their own virtual GPU, get all the rendering done in hardware rather than in software, which is what we're doing today, and then remote it out to the user. And there's some really exciting stuff that's going on in this whole space that's going to improve performance going forward. So wanted to include that one. Okay, so we now get to the exclamation point. Give me an exclamation point. All right, you guys have been a good audience. I like this. So then we got a whole bunch of other stuff. And quite frankly, I don't even know what half of this crap is yet. Okay? There's someone who insists to me I have to spend time looking into something called Windows 7 transparent caching. Anybody know what that is? Yeah, I don't either. Okay, but I'm told I need to look at it. So the operating system at this point is so old, and they've put so many different things into it to try to improve performance. That's a very, very complicated system. And I'm kind of hoping that we're going to get to a point that they can start to simplify and start throwing some of the crap out that we don't need, particularly as technology changes and it doesn't make as much sense anymore. I mean, the Ready Boost is, why that's included in Windows 8, I don't really understand, right? Who's going to use Windows 8? They're going to be on a tablet, They already have a flash drive there. Why are you going to do that? I don't know, but that's where we're at. Yep, with Vista, which was the appropriate point, right? The hardware we had when Vista came out was underpowered for the job. We had nowhere near enough memory. We had very slow hard drives. USB memory was cheap. It's still cheap.
The Windows 7 transparent caching is, I think, folder redirected folders. They are cached automatically.
Yep. Which, okay, so good or bad thing? Do you have any problems with? Have you seen any problems with the cache coherency when you do that?
We only have problems with our PSD files that are cached, and then they open Citrix with the same PSD files, and we have a version offline and on the Citrix server, things like that. But for the rest, it works fine.
Okay. Sean Bass routinely refers to folder redirection as a disaster waiting to happen. He really hates that technology. And basically, he's had some bad experiences where, due to the fact that folder redirection didn't work, you suddenly have 1,000 people down and performing very, very badly when they do try to do anything because it's waiting for the timeout to happen for a folder that's not there. Right? Application manifest caching. This is an area that I've actually looked into for my AppV purposes a little bit. So if you have an executable, a newer .NET style executable particular will have a manifest file embedded within it. And apparently the operating system does a little bit of caching with these things. But I've actually been playing with some older applications that didn't have a manifest file, that needed elevation, and they didn't have a way to trigger it because it was an old enough legacy app. And it turns out you can manually create your own manifest file. So if it was foo.exe, you just create an XML file called foo.exe.manifest, put it in the same folder, and you can add in the syntax to say, oh, this application requires elevation. So now when you run the application, they'll automatically get the prompt and get elevated after they put in the password. So even if the app wasn't designed for that automatic elevation, we can get it now. We don't have to train them to right-click, run as administrator to run that application. Credential caching, this one comes into play in, I run into this all the time with people doing AppV sequencing. So they create a VDI image to do their sequencing, and the process is you install an application and do all the capturing stuff, and then you revert your VM. So when a machine joins the domain controller exchanges a password with the machine so that the next time it boots up, it just provides that password, and the domain says, okay, you're good to go. By default, every 30 days, the password changes. So if you're in a VM environment where you're constantly going back to a snapshot, after 30 days, you boot up, it's going to do the new password into your VM. The domain controller is going to remember it. The next time you revert, that machine's no longer in the domain properly. And you have to drop it out of the domain and drop it back in. So we've learned over time to actually disable that caching feature for the password. Okay, and that is the end of my time, except for questions, right? I got time for questions? One? One question. Make it a good one. Any questions? Yeah.
One, you talked about the file directory cache, the MFT dollar.
Yeah.
We have at the moment a problem that sometimes it is on network drives, I think, mostly. When we rename a folder, it doesn't happen. You have to do a refresh, and then it happens.
That would be exactly that case. It's still held within the kernel memory there. Now this is a map drive as opposed to a remote folder, right? Yeah, that would exactly be the case. You need to flush that out, and I have no clue how to make that happen faster. No. No. Maybe some. Okay, so I will have a book by this name coming out at some point. I'm a little behind schedule, so it's not done yet. But if you want the gory details on a lot of these topics, you'll end up finding them in there. So thanks for, yeah?
One question more about the book. Will it also be addressing ways to enhance the caching that is possible? Not all caching types discussed are in the hands of the user, but some are actually tweaked for that.
Yeah, it does cover some of the tweaks, and in particular, it really focuses on a lot of the tools around it. But shall I say, most tools are monitoring. It will cover some of the tweaks. Most of the tweaks, quite frankly, are really around disabling the features as opposed to enhancing them, unfortunately. And I can't really, off the top of my head, remember any of them that are in there. But if there are some, they're probably there. Okay, well, thanks for coming. I'll be back tomorrow, I think in the morning, and we'll actually go through the full Windows 7 and Windows 8 boot process, including hibernation, sleeping, and all of that stuff. So thanks for coming.